Okay, welcome everyone. Today is January 21st, 2017, and welcome to the John Chappell Natural Philosophy Society Philosophy Science Chat. So you can probably see my first opening screen here, and this is our little ad to encourage you to renew your memberships and to take advantage of the other things that we have on social media. Okay, so this morning, I see we have Hans here this morning. So one of the things that we had discussed last time was he had a flowing ether theory that he's got a new paper on. So I was wondering whether Hans, you'd like to start the discussion about that.
Well, I have gone further. I think I update my papers on a daily basis, and so I'm still proceeding. I was triggered a bit by Duncan, his paper. Duncan has written an article about Aether, and I wanted.
Yeah, actually, I was kind of mistaken about that. Yeah, but go ahead. Yeah, we were going to talk about Duncan's paper, but go ahead.
And as a kind of response on that, I've added a new journal page about Aether and fields on my docs.com site, and where I discuss what the difference is between fields and Aether.
All right. So what is different in Ether?
Well, I'm not using Duncan's idea of Aether, but more or less the idea that Lawrence had about Aether. Lawrence had also an idea of Aether, and that comes very close to what one of the two views that the Hilbert book model gives. The Hilbert book model gives a storage view and it gives an observer's view. And the storage view comes very close to what Lawrence did with his Aether. The Aether of the storage view, the structure is an Euclidean structure, while the observers see space-time structure. The Euclidean structure is using quaternions to store data, and it uses proper time. And what the observers see is space-time that has Minkowski signature, and that space-time structure uses coordinate time. That's also what is used in the Maxwell equations. And so I wanted to make, this is the article that I have added, I think it was yesterday or the day before, to my site.
Yeah, so this is hot off the presses.
What?
Hot off the presses. You just came.
Sorry, you mentioned coordinate time. Simply the parameter t rather than something like ICT. Is that right?
Yeah. In fact, the real part of quaternions can act as progression, can act as proper time. And the symbol that they usually use is tau, the symbol tau, the Greek symbol tau. And t is normally used for coordinate time. And these two have a relation with each other.
All right. Well, I see we have Duncan with us today. Good morning, Duncan.
Good morning.
All right. Well, we started off the discussion. Hans had some comments about, and in fact, he came up with a new paper. But I believe that one of our topics today is that we're going to discuss your paper on outflowing gravity. I see we also have Neal Adams here today. And we'll also try and get to discussion of his theories about the expanding Earth. But let's growing. Okay, so Duncan, would you like to lead us in a discussion of what your paper is about?
Yes. This is a paper that was published in December of last year. It's entitled Outflowing Ether. It's the third of a trilogy published in Physics Essays, all of which together set out a proposed concept, I call it, of gravity. The concept is physically based entirely. It basically is involved with ether flowing into the Earth and exerting ram pressure on any atomic matter that it strikes as it flows into the Earth. Implicit in the theory, or explicit in the theory, is that there has to be outflow. Because unless there's outflow, the well of ether in space would diminish and gravity would cease to exist. So it's a cyclic theory. There's inflow and outflow. There are two different types of ether that are involved in this concept. The outflow is of individual ether cells, and the inflow is of, in effect, liquid ether. Put another way, it's ether that has turned into, or changed, condensed is the word, into droplets in space. And the droplets of ether are combined, are a combination of God knows how many, but let's say billions of ether cells that go into a particular droplet. This distinction is key, for it provides an explanation as to why gravity is a one-way force. Because the outgoing ether cells are tiny compared to the incoming droplets. And when you apply that thinking to atoms and molecules, which are made up mostly of space, you can see that the outgoing ether cells will have a far greater tendency to go right on through an atom than the incoming ether droplets. In a way, you can compare it to a fish net. Depending on the spaces in the fish net, minnows will probably go right on through, but larger fish will have a far greater tendency to strike the net. So therein lies, at least in my papers, the explanation as to why gravity is seen as a one-way force. There's acceleration. The incoming ether, as it flows from space and moves towards a cosmic body like the Earth, accelerates because, in effect, it's moving from a broad expanse into a narrow space, the Earth itself. And anything that flows from a broad expanse into a narrow gap has to accelerate. Take a look at a slow moving river, and as it heads towards a canyon, it accelerates. So there's a very basic physical explanation for acceleration. Why the flow? Well, if you look at the Earth, for example, as a giant vacuum cleaner, a vacuum cleaner operates on the basis that it expels air. In doing so, it creates a partial vacuum in the vacuum cleaner, and the ambient air that surrounds flows into that partial vacuum. Well, I suggest here that it's in effect the same thing insofar as this flowing ether approach to gravity is concerned. The speed of ether that's coming into the Earth. In an early paper, I suggested there might be an experiment of dropping something from a spaceship and letting it go back to the Earth and check its speed. Well, at a later time, I found that it has in effect already been done. It's been done by the spaceships that go from the moon to the Earth. When they leave the moon, they're accelerated to just enough speed to get them over that dividing line between the dominance of the moon's gravity and the dominance of the Earth's gravity. From that point on, no power is provided. The moon ship coasts back to the point where it meets the atmosphere of the Earth, and at that point, retro rockets are needed to bring the ship under control. But there's a tremendous distance where the moon ship is doing nothing but coasting. And my suggestion is there is a good indication of that flow of the condensed cells from space toward the Earth. Now, another aspect that I think recommends this approach is this rather peculiar fact that the force of gravity between the Earth and the sun is directly in line. It's not like light traveling from the sun to the Earth and we get it 8+ minutes later. It's not directly in line to start with, but it gets to the Earth. But as far as gravity is concerned, it's directly in line. How does that fit with this concept of gravity? Well, it fits this way. Keep in mind that the flow of ether from space toward the sun is directly at the sun. And that's the major contributor to the vacuum cleaner effect, bringing ether or condensed ether toward the solar system and particularly toward the sun. Now, as that ether is coming in and reaching the area where the planets orbit the sun, and in particular the planet Earth, what direction is that ether going? It's going directly at the sun. And if it's going directly at the sun, there is an obvious explanation as to why that the force of ether is directly in line rather than 8+ minutes out of line between the sun and the Earth. The Michelson-Morley experiments why doesn't this, the Earth while in orbit, get affected by flowing or driving through the ether that is heading toward the sun? The Michelson-Morley and similar experiments haven't excluded this force against the Earth in its orbit, but have produced figures that are way below the approximately 30 kilometers per second I think we would expect from the orbital speed. The answer to this is that the Earth and other planets and the sun, etc., are likely cocooned to some extent by the ether that surrounds them. Let me put it this way. You're in a car and you're driving at 60 miles an hour. You don't feel it. You're inside the car. Open the roof, then you do feel it. But the car feels it. You don't. All the experiments, the Michelson-Morley experiments, have been within that car. They've been on Earth. They've been inside the cocoon. So would you expect to get the full slowing down effect that you would otherwise get if the ether that's coming toward the sun is having its full effect on the Earth? So those are a few things that surround this theory. The latest paper, the one just published, Outflowing Ether, tackles the outflowing aspect of this concept. And it tries, we'll put it that way, to come up with what causes that outflow. I've given you a reason for the inflow, a pressure imbalance between ether and space and ether and Earth that's been caused by the vacuum cleaner effect. But what causes the outflow? Well, this paper tackles that, and it argues that heat derived from the ram pressure of the inflowing ether causes it to vaporize or evaporate into gaseous ether. In other words, individual ether cells. And that gaseous ether flows into space mainly by way of convection, propelled by the force of buoyancy, and partially by way of diffusion. And that is the guts of the paper that's just been published. So I don't know whether my explanation has been brief or otherwise. The papers are a lot longer, but that in substance is the concept of a physical cause of gravity that I've come up with.
All right. So I'll open it up to questions. Does anybody have any questions?
Well, I just have a couple of points, if I may, Franklin. I've had a quick look at your paper. I have it in front of me here, in fact, and it's an interesting exposition. But it appears to me, and also from what you've said, that it's rather qualitative. I mean, you've given some reasons as to why gravity acts in such a way, outflow and inflow. So I'm just interested, have you any quantitative aspects which could be the subject of testing by experiment? So that's my first point. I just have one or two other points, perhaps, just raise them. When you were talking about the effect of gravity, or the force of gravity basically being in line, unlike the light, I'm just wondering, have you sort of estimated an equivalent speed of gravitational interaction? And my last point was when you were sort of explaining the small results, practically null but not null, of things like Michelson-Morley via sort of a cocoon around the Earth. How would you sort of explain the positive results you get from a sort of a Michelson-Gale experiment?
Okay, I'll try to tackle those. I'm just making a note or two. First of all, the observation that my work is essentially qualitative, that's dead on. It is essentially qualitative. Are there any tests? Well, there are a number of things. The moon ship coming back to the Earth, the figures are there. The speeds are there, but it's a qualitative jump from that ship to the proposition that that ship is actually being transported by this inflowing ether. I can't prove that, but those figures are there. The direct line of gravity between the Earth and the Sun, I think that's a fact of life since the days of Einstein, not Einstein, Newton. And but I can't go further than that. That's an idea. The acceleration aspect, flowing from a large area into a smaller area. That again is a fact of life. But to actually get down to figures, I can't do it. And I'm not a mathematician. That's not my background at all. But so my approach is basically qualitative throughout. I've been trying to come up with an idea that is physical, that has a lot of things surrounding it that give it at least an air of substance. And that's why I look to these things, the moon ship coming in, the river flowing into a canyon, the minnows and fish through a fish net, etc. Those things that I came up with. To translate those into mathematics, I cannot. As far as the mathematics is concerned, that is not mathematics. Michelson Morley. How do I explain the positive results? Explain them because even with the Earth in a cocoon, it's not as fulsome a cocoon as the person sitting in the enclosed car driving at 60 miles an hour. It's an aspect that would be taken into account to determine how much slowing down there would be and how much of that would be felt in an experiment on the Earth. And it seems to me that some of it would be felt on Earth, but not a great deal. Most of it would be felt by the cocoon surrounding the Earth. And qualitative, but there's the idea. I hope I've answered the questions as best I can.
Well, just very briefly, it does, thank you. And I think it might be an interesting exercise, perhaps by others, to take your ideas and model them mathematically and maybe try to make a couple of predictions which could be tested. Just on the very last point, I see what you were saying, essentially that the entrainment, if you like, of an ether would not be absolute. But I was also asking not necessarily why you didn't get an absolutely null result from the Michelson-Morley, where you're testing against a 300 kilometers per second, as you say, the orbital speed of the Earth around the Sun. But I'm talking about the Michelson-Gale-Pearson experiment in the late 1920s, where they tested against the rotational speed of the Earth, maybe hundreds of kilometers per second, and they got a full result there. Are you familiar with that one?
I hear what you say, and I before I comment on that, I think I would like to read that paper and have it in mind. So I don't think I can go further at this point.
Okay, thank you very much.
I'm new here. Can I ask a small question?
Sure, go ahead, Neal.
Okay, if we assume that this ether can go inside the earth and be contained to expel it out, then presumably as much ether can fit inside the earth as can fit into space, which basically says that there's the same amount of ether out in space as there is within the earth per square foot. Therefore, what attracts the ether in? In other words, if the earth can hold as much ether as the same volume of space, space can hold the ether because it takes it in and then holds it and expels it out, then at some point the same amount of ether is held inside the earth as in an equal volume of space. What is it that, in other words, we're talking about gravity, what is it that attracts it in if it's already filled with ether?
Okay. Thank you for the question. I don't conceive of the ether being of the same concentration everywhere. Indeed, I see it otherwise. The expulsion of ether from the earth, I liken to the expulsion of air from a vacuum cleaner. That's an essential part of a vacuum cleaner. That is the expulsion of air. That expulsion of air reduces the concentration of air within the machine, and that creates the difference in concentration of the air, the ambient air in the room that you're vacuuming, and the air that's actually inside the machine. It's that difference in concentration that is absolutely key.
But that's not true, is it? I mean, there's an engine that takes that air and expels it out. In other words, there's another force that's in your vacuum that expels the air out, so and therefore makes the vacuum to bring it in. So, what is your mechanism to expel it out while you have a mechanism to pull it in? It basically, it sounds like you're saying it's gravity, like it's
No,
gravity that pulls it in, and then there's something else that throws it out.
Okay, sorry, I'm having difficulty hearing your voice, but I see what you mean by the difference. A vacuum cleaner has an engine, but a and a cosmic body does not have the same kind of an engine, but it has a way of expelling ether, and that when the ether comes in and it hammers the earth, it brings with it a lot of energy, and that energy breaks up the liquid ether, breaks it into ether cells that are energized, and those ether cells being energized are in effect thrown out of the earth just the same way as H2O is expelled from liquid water. H2O molecules are expelled from liquid water and head up into the atmosphere. And that's a fact of life. And it's an aspect of this that I look to at least to give a sort of comparison. But that's going on all the time. The water, liquid water gets heated, it expels the H2O molecules, and up they go. Now, there's the engine. You're asking for an engine.
Yes. So you're saying the heat from the sun is the engine that expels the H2O or the water molecules up into the sky. What is the engine that pulls in and expels the ether? Is it? I mean, it's not H2O. What is it?
Okay, the engine that pulls in the ether.
And expels it.
That is the pressure difference within the ether in space and inside Earth, okay, inside the vacuum cleaner.
So you're saying they're not equal. There's essentially a vacuum of ether inside the Earth, and that vacuum sucks ether out of space into it. Then if it does that, then why does it expel it? You would think then it would just stay in there. Just asking.
Well, I see your question. I don't agree. I think the stuff that's coming in is got one hell of a lot of energy, and it's striking continuously, ram force, against the atoms in the earth.
Mm.
And that is energy which creates heat, which expels which not only creates heat, it breaks up the uh, the incoming ether droplets, breaks them up. I'm sorry, I couldn't make out, but there are two different processes going on here. In effect, as in a vacuum cleaner, there is the expulsion, and then there's the other side, which is the inflow because of a difference in pressure.
All right, good.
Okay, thank you.
Do we have any, do we have any other questions for Duncan? So far we've discussed about whether there are any quantitative predictions. So, but I wanted to ask you, Duncan, so in the spaceship example, so what exactly are you expecting? Are you expecting that the spaceship will tell us, because the spaceship presumably cannot go any faster than the ether flow? Is that what we're predicting?
It actually, when it enters the space, which is essentially the dividing line between the dominance of Moon's gravity and the dominance of Earth's gravity, it's got excess speed. Not a lot, but it's got excess speed. Point. It's got to be going faster than the flow, or probably going faster than the flow of gravity to the Earth. But after a period, and probably a very short period, there will be equilibrium, as I see it, between that flow coming into the Earth and the moonship. And from that point on, it's just riding. It's riding the flow. Maybe right, maybe wrong. But the interesting thing about it is the figures of the acceleration, the different speeds of that spaceship as it proceeds through the part of its trajectory that I've been talking about, they are known. I've referred to them in, I think, I forget which one of the three papers, but I've got them. And
So would you predict that there'd be like a maximum speed, like if an object obtains the speed of the inflowing ether, that it wouldn't go any faster than that? So there would be, I mean, that's very different than what we would normally consider acceleration, which applies no matter what.
No, so, I would consider what is happening on the return trajectory as being purely and simply free fall. And I would say if it's free fall without anything of substance to affect the free fall, because there's no air in that, so it's just straight free fall, and it is accelerating during the free fall, and the figures show that acceleration. So my thought is there's a good example of something that is simply in equilibrium with the surrounding ether. And that surrounding ether happens to be flowing, it happens to be accelerating, and so is the moon craft coming back to the Earth. But it's just a matter of equilibrium. It's riding in free fall.
So what would you predict? Would there be a difference between that and conventional mainstream gravity, or would it be the same? Because I'm pretty sure that if they would have noticed something that wasn't like Newtonian, they probably would have said something.
No, I would not predict any difference between that and mainstream gravity. I'd say that you're observing gravity.
But that would make it difficult to determine who's right if
Pardon?
both theories produce the same thing.
Yeah, okay. No, I absolutely see it. But what you mean, but at the same time, there happens to be something happening out in space which is being kept track of accurately, which is in free fall. It's not being accelerated by any engine on board that craft. It is in free fall. All right. If you buy into the approach to gravity I've taken, it seems to me that's some indication of the inflow and the acceleration of that inflow.
Well, in order
Because
to, my point being that in order to convince other people of that,
yeah,
I think you would need an experiment that your inflowing gravity could explain, but that conventional theories could not. So, for example, if you knew exactly what your ether particle was and you identified it in an accelerator and you say, aha, there it is, I can see in my experiment, it's there, and then that would, no, conventional gravity doesn't have anything like that, so there'd be no way they could explain that. And I was just wondering, what can we experiment on that might show this to be correct?
it, Franklin, I do not know what you mean by conventional theory of gravity.
Well, that would
I
just
don't.
be an attractive force 1/r², depending on the masses.
Okay, you're into the mathematics, and you're saying an attractive force. All right. If it's an attractive force, what's doing the attracting? What physically is happening? And I really, in a way, I don't care whether you call it an attractive force or a pushing force. Well, I do care because I think it is a pushing force and not an attracting force. But I do not think uh, of it being of using the word attraction when I can't see anything out there that could be doing the attracting. I can't see it mechanically working that way. Can you?
Well, we do have our own earthly examples of attracting. We take two magnets, north and south, we can see those attracting. Or if I take two pith balls and I charged up one positively and one negatively, we can certainly see attraction happen in those instances. So
No.
definitely things like attraction do appear to occur. I would give you as examples.
You're looking like science is looking for the replacement for magnetism, and science says there's such a thing as a gravitron. I don't personally believe in it, but essentially you're saying there's a much better example in magnetism, and until we find something equal to that and are able to identify it and to see it and to know it, then we're still, fishing around. We know the action. We know the action is a pushing or pulling force, but beyond that, we have no scientific evidence of what that is.
Harry Ricker, I want to interrupt again, if you don't mind.
Go ahead, Harry.
I discussed this in my papers at the General Science Journal that discusses the history of magnetism, and which it's pretty clearly demonstrated there that the idea of gravity evolves from magnetism. So Kepler thought that gravity was a magnetic force. So until you address the issues of the nature of magnetism and electricity and how it relates to gravity, I don't see how you can make any progress.
I agree.
Yeah, there are a number. I mean, there I guess two major camps. So Duncan is in basically the pushing gravity type. This is very similar to Lesage gravity, though the Duncan adds in this special. His contribution is that he's saying that not only does that ether come in, but it also flows out. That at a different format than it flows in. So he's kind of explaining away, why doesn't the Earth burn up instantly due to all this incoming thing? So that's an important part. And I've never really heard suggested that things are flowing out. And it kind of solves the problem of, there's no vacuum cleaner that can continuously suck in materials and never ever spit it out again, right? So so I can see how his theory is kind of solving some of those. But on the other hand, there are people who do think that gravity is actually an attractive force. My own theories say that gravity is literally the electrostatic force.
Could I jump in just for a second?
Go ahead.
This is Jack Kirkendall. I'm going to agree with Duncan Shaw on that it's a pressure, and I would suggest that both quantitative and mathematics are, by these theories, are already done by Xavier Borg and by Francis Fernandez, and they both come up with the actual particle and its mass. And then a third thing you need is the definition of heat by Professor Karnarev from Russia. And you get rid of the heat problem altogether because of the mass of the this particle that creates the pressure. So three things: Karnarev, Borg, and Francis Fernandez actually would have quantitative numbers and a full theory on the pressure gravity. And I'll leave it at that.
Yeah, that's true. The Lesage gravity has been worked on for hundreds of years by many people, and you're right that if you work it out mathematically, you can make it work. I don't think there's any question about that. Although what Duncan has, like I said, is unique in that he's suggesting that there's this outflow.
The outflow thing then should produce heat. And does Duncan, do you have any idea of the temperature of this heat above absolute zero?
I would expect that when this outflow at least gets into space, it would be very close to absolute zero. And I would, amongst other things, have in mind in saying that what is the temperature that is associated with space, which is what, 2.4 degrees or 0.24, whatever it is. It's very close to absolute zero. So but the actual heat, say, for example, on Earth, when this transition takes place, the hammering, the ram pressure from the incoming stuff, the changing of the droplets into individual ether cells, and that temperature, I got really no idea what it would be. I expect, though it's not very high, I have in mind, for example, the Earth, of course, has got a lot of heat, but a lot of other cosmic bodies do not. And yet they are, have to be, as subject to this process that I've been describing as the Earth or as the Sun, and yet there isn't the overall heat. Some of those, I guess, got to be pretty close to absolute zero, and yet there's still this process of striking and changing state from liquid to gas, in effect, and expulsion that's going on at that point. So it's got to be a fairly narrow window, but it's got to be, for example, it's got to be enough to overcome what Maxwell and several others have predicted, that at least they have for the Lesage theory, which I am not an adherent of the Lesage theory in any sense other than it's a pushing theory, and mine is a pushing theory. But back to Maxwell and others who say the the heat that would be exercised by in the Lesage theory would be enough to burn the Earth to a crisp in seconds. So there's got to be some way for outflow to handle and expeditiously the potential heat problem from the round pressure of inflowing ether.
Any other questions for Duncan?
May
I do.
may I ask something?
Go ahead.
Hans Verleunen. What happens for an object, a massive object that is in free space with a uniform speed and then starts its propulsion rocket suddenly so that it accelerates? What we normally have in physics is that you get inertia, a force of inertia that draws any person in the rocket back to the back end of the rocket because it has accelerated. How do you explain inertia in free space?
I've written a paper on inertia and it's included on my website, which is www.duncanshaw.ca. But looking at your question, at least through my eyes, you've got a spaceship that is encircled by ether. If it's in the ether, for example, that is in the area that is where the gravity of Mars is dominant, for example, it will simply ride that ether. But if it accelerates and gets into a situation where it is no longer riding, accelerated beyond whatever the ether flow happens to be, as I see it, it's going to slow down. Once the acceleration has stopped, bit by bit, it's going to be brought back to equilibrium, that equilibrium being the state of the particular, of the flow of the ether that it happens to be in at the time. And if it's heading toward Mars, for example, and it's accelerated, it's going to slow down until it again is equal to the velocity of the flow of the ether that is heading toward Mars.
So the action of acceleration has a dependence on the direction of this rocket.
I'm sorry, I haven't got the essence of that. Could you try it again?
Well, if you accelerate in one direction and the ether is flowing in that direction, it will differ from the case that it's accelerating in the other direction than the ether is flowing. So how do you explain the difference?
I'm trying to understand, but as I see it, it doesn't matter what direction it accelerates, forward, backward, sideways. It's once the acceleration has ended, then bit by bit, the flow of ether that it happens to be in at that time is going to take over that machine and bring it back into equilibrium with that flow.
So it decelerates the rocket until it is in the same uniform speed that the ether had.
Yeah, if you decelerate the rocket, for example, as I see it, that rocket is slowly going to be accelerated by the ether that is flowing past it because it's been decelerated, it's flowing past it. It's going to be inevitably brought back into equilibrium with that flow of ether. So if it's decelerated by the retro rocket, it's going to be, once that retro rocket is spent, then it will be brought back into the ether flow and will flow at the same rate as the ether.
Such effects must have been observed on the trajectories of satellites that are sent around in outer space, isn't it?
Yeah, I think you're right. And as I mentioned earlier, when the moon craft leaves the moon, it's accelerated to break moon's gravity. It's brought to a speed which is more than is necessary to get it into the dominance of Earth's gravity. And as I recollect, I looked at these figures, and I'm not absolutely sure at the moment, but as I recollect, the process that you've just mentioned actually occurs.
Yeah, but I'm talking about free space, not for a rocket that is leaving the moon. No, something is acting in free space and then starts its rocket and moves with some other speed. And what you say is it's bringing back afterwards its speed back to its original uniform speed. Is that observed?
Not exactly. The uniform speed, I would replace that with the speed of the surrounding flow of ether.
Yeah, but that means that any object in space that's flowing around there is must travel with the same speed as the ether is flowing.
Yes.
Well, I suppose the prediction here would be,
for example, if there's a orbiting the Earth, you've got a Sputnik, etc., orbiting the Earth, and you've got that combination between centrifugal force, I believe it is, and the gravitational flow.
But that's not free space. That's something around some a very heavy object. Otherwise, you won't have centrifugal space or something like that.
Yeah. Well, I see, but I think of the space, most of the space between the moon and the Earth as being in effect free space. What's in it?
Yeah, there's the moon in the neighborhood. There's the Earth in the neighborhood. If you go much farther away between galaxies, there's nothing, hardly anything. And there, you can put a question that I just put about a spaceship that's flowing there and starting its rocket. And what happens then? There is no big star or a big planet in the neighborhood.
Well, I'm not sure you're right. When we look at what's happening, take our own galaxy, for example, there's interaction between the stars in our own galaxy. They're moving in unison.
But all these things move in different directions.
Well, there are different directions, there are different processes going on, but generally, a spiral galaxy like ours has a overall coordinated movement to it, and then you get from just one galaxy like ours, you get into clusters of galaxies, but they are clusters.
Yeah, but
coordination.
In these free spaces, you can go any direction that you want, and your ether would force it to flow in the direction and at the same speed of the ether, that the ether is going, and that's not observed, to my opinion.
Mm-hmm.
We have sent satellites in such spaces far away from the Earth.
Well, I think I've gone as far as I can on that one, Hans.
Thank you. I want to put that question because I think that's a problem with your theory.
So I was wondering, so if you're in a spaceship returning from the moon and you're in the moon's flow and you are in, so you're traveling at the same speed as the inflowing ether. Now, if the astronauts then turned on their rockets, so they were going faster than the inflowing ether, and then so that their velocity is now faster than the inflowing ether. So the inflowing ethers is say going 6 miles per second, and now the rocket ship is going 10 miles per second. Now, when they turn off their rocket ship, what would you predict would happen to their speed? So they're going faster than the inflowing ether. What would be your prediction?
I would find that a tough one because it's not a straight on situation, because approaching the moon, you wouldn't be going directly at the moon, because the object of the exercise is to get into moon's gravity and then using it so that the moon can be orbited. And but if it's a straight on situation, and the inflow is 6 kilometers and the acceleration puts it to 10, you probably got a problem on your hands. You're going to slow down. You've got to slow down back to the 6. It may take quite a while to do it.
Hold on
And when you're into the questions that are faced all the time on returning to the Earth, for example, there's got to be very minute and detailed calculations as to exactly what will happen when you slow down.
But what about momentum?
You need some pretty big computers to make those calculations.
Well, I mean, that would be a difference that you could actually test, because under conventional gravity, even though you were at 10 miles per second, you would continue to be accelerated even after you did that. But your flowing ether would predict that they would actually start slowing down. So that would be an experimental difference. Go ahead, Neal.
Talking about momentum. In other words, you have momentum. Your momentum is added to whatever the gravitational, whatever this inflow is. So you can't discount momentum. You're already traveling twice as fast as the inflow is. You're going to continue that, and your inflow is whatever your inflow is. Your momentum is the thing that you're adding, which you add to the inflow. You can have momentum. You can take momentum and take it in the opposite direction of the inflow. Momentum is basically what your rocket is causing by driving your rocket in any direction, overcoming whatever this gravity. In other words, we're overcoming gravity all the time. Okay. And that's what we call momentum. That comes from whether our rocket or walking down the street or whatever. So momentum is added to your inflow. So you're fine in as far as that's concerned. You're not going to slow the rocket down to the inflow of your particles. You're just going to add the momentum to that. Yes?
No. Okay. I say yes and no at one and the same time. Yes, of course, you got momentum, but at the same time, you're out of kilter with the flow of gravity. And that gravity is bit by bit going to bring you back into equilibrium with its flow.
But we know that's not true.
But you know that's not true. I don't see it that way.
Well, if you have a rocket and it's plunging toward the Earth, it's not going to slow down to a standard speed. It's going to continue, because those are the rules of gravity, the rules of falling bodies. So that's going to take over. Momentum is you can add momentum to gravity anytime you want to. You can jump out of a window, and when you jump out of a window, kick off the windowsill, and now you're going faster than whatever your falling force is. But even your gravity and your particles in other words, rules of falling bodies, it accelerates. It doesn't go at a constant speed. You accelerate, yes? And momentum accelerates you. So you have two forces involved here: your basic theoretical force, plus you have momentum.
Well, I've tried to answer that, and you drop the little ball and the big cannonball off the leaning tower of Pisa, and there's a big difference in momentum, but there's not a big difference in the falling speed.
Well, I think that's an experiment you could do. You could go to a very tall building, and you could build a device that has a rocket engine on the rear side, and you can push it further, faster than the natural falling speed, and the prediction would be is that if mainstream gravity works, it will go faster still, but if it's flowing gravity, then it would be exceeding the flow of gravity, and it should actually not go any faster at the very least, right? If it's going faster. So that's an experiment. Now, personally, I would think that that when you did that experiment, that you would find that it went faster, that it didn't matter that it exceeded the free fall speed. But that's something you could pursue.
I don't see that conflicts with the theory. The theory works either way. I mean, momentum is a separate force. It has nothing to do with this, with the force that you're talking about, or that replaces gravity. Momentum, gravity is gravity. They're two separate things.
I think it's more like if you have a cart that's on a sail and you've got a 10-mile-per-hour wind, it's like the maximum speed that thing can attain is 10 miles per hour. Right? So if your cart has a motor on it and it's going 20 miles per hour, the 10-mile-per-hour wind is not going to do anything to you. In fact, it would probably slow you down, I think is the point.
Well, on that point, Franklin, accelerators on Earth, the major accelerators, they can do a good job of accelerating, but there are limits. And I suspect the main limit is that you're pushing against ether all the time as you accelerate. And there's a point at which the resistance of that ether is so immense. You're hitting so many droplets of ether that you just can't go any faster. So if we can get up to 99.9% the speed of light, we can't go beyond that. And up in that area, the amount of energy that's required for any incremental boost of speed is immense. To me, that is indication that acceleration process is up against something that has become very solid. Just like air becomes almost solid when you accelerate to a great speed. If there are ether cells in there, if there's a medium of ether, you got limits on your hands, or potential limits, that you got something that's going to make further acceleration extremely difficult.
The inertia on Earth is only dependent on the mass of that thing which is accelerating. It's not depending on other things. At least if you are not traveling through gas or a liquid or so. If you accelerating in vacuum, then it's only depending on the mass of that thing that's accelerating.
Yes, it seems to me, to a certain down here again, that you're thinking something analogous to the resistance that one obtains from air. I mean, if you drop an object from high enough above the Earth's surface in free fall, well, it will reach a terminal velocity when there's a balance between the air resistance force and the the downward force from the moving object. So obviously, if the moving object has some additional boost, well, then the terminal velocity will be different. The terminal velocity will be greater. But in each case, you're acting against the air resistance. And it seems to me that your discussion or your description of what's happening with sort of an ether force is maybe analogous to that to a certain extent. Is that so?
Well, I would say that the terminal velocity is going to be the same, no matter no matter that you might give it some extra boost. You got two things falling toward the Earth, and there's the atmosphere. You give one an extra boost so it goes faster. I would say that its terminal velocity is actually going to be achieved a little later than the terminal velocity of the other. Terminal velocity. It's going to be pushed toward the Earth by inflowing ether, and it's going to be resisted in its movement toward the Earth by the encountering of the atmosphere. And I think it's those two things that are going to, in the end, be what's required for the equilibrium. So we're almost on the same wavelength, but I think not quite.
That's another experiment that could be done, actually, which would be of interest.
So it looks like we have a flag raised by Cornelius. So why don't we get one final comment on this? Cornelius, are you there?
Yeah, can you hear me okay?
Yeah, we can hear you okay.
Okay. Well, one of the questions I've always had with the flowing ethers, you're talking about the ether flow and the flow direction, but out in space between the planets, between the stars and that, ether is coming from all directions at once through any particular point in space you choose, in order for it to flow towards the planets and that. But if ether is a massive particle that has a pushing capability when it strikes matter, how is it that the ether particles themselves do not interfere with the ether particles themselves? I know of no fluid in which particles of that fluid can flow in all directions simultaneously and maintain any consistency in direction of flow. Basically the flow becomes terminates. It stops. How is it the ether particles continue to flow?
Cornelius, I think what you've been saying is the substance of the Lesage theory, which has particles in space going every which direction all at the same time. They're crisscrossing all the time. My approach is no, that's not so. There's a flow in space, and the flow in space is of ether toward cosmic bodies. And there's a big difference between crisscrossing and a flow.
The flow in space is from the ether particles from the moon towards the Earth, and the flow in space is from the Earth towards to the moon. They collide. They directly, if you're going to have pulling or ether forces towards the Earth from all directions and ether forces towards the moon in all directions, somewhere along the line, those ether particles have to be going directly against each other. And certainly so they have to be flowing in every direction at points in space between the planets and between the devices. There's no way physically or no logical way that you can conceive of any other way for particles to flow. They can't. Otherwise they would have to just disappear somewhere magically above the Earth and begin to flow towards the Earth, and just circumvent the moon entirely. So that means that somewhere out there they just disappear and start flowing towards the Earth with velocity of the speed of light. I can't logically conceive of any way that geometric and that's one of my biggest issues. The other issue is that if ether is a fluid-like substance, there's no way that transverse waves, which are light, flow through a fluid-like substance. And if it has viscosity, then that viscosity causes drag on anything that goes through it, and so nothing can flow through it. So you can't have mass through it flowing through something that can also support light.
Shall I answer?
Briefly, we would like to move on to our next topic with Neal Adams, but why don't you go ahead and summarize and answer that question?
I'll give a short answer as I see it. You land on something of substance. That I have no doubt. But the concept I have is that you do have different things going in different directions. You've got the liquid ether flowing into the earth. It, you've got individual ether cells going in the opposite direction. Will there be some colliding? I don't see how that can be avoided. There will be some colliding. They're both occupying territory, and once in a while, and I don't know how often, they're going to have to hit. At least that makes sense to me. How much is another thing altogether, and how they keep going, and the outflowing ether paper addresses that. I still think, though, that this inflow and outflow is quite different from the Lesage approach, that there are these tiny things that are always crisscrossing in space. They're not flowing, they're crisscrossing at random. And the approach I'm taking is, this isn't at random. These are being guided, and they're being guided, amongst other things, by pressure differences. I think that's my summary.
All right, thank you very much, Duncan. And so I encourage you to read Duncan's paper. We did have a link to it in the email. And our next topic will be led by Neal Adams. So Neal, would you like to tell us about, you say the growing Earth. You didn't seem to like the term expanding. So why don't you tell us about that?
Sure. That term expanding Earth came from Samuel Warren Carey in the 60s, geologist. And of course, being a geologist, he's not going to say necessarily, if he sees the Earth getting bigger, he's going to say expanding, but he's a geologist, and there's really no such thing, as far as I know, as anything expanding. Nothing expands. And as I understand it, that's sort of a principle. You essentially don't expand unless there's some other force that's added. You can expand if you add heat. You can make a balloon get bigger by adding air. You can make an explosion get bigger by putting chemicals together and igniting them. But essentially, nothing expands. Things either stay the same or they grow. Physics does seem to have one exception, the universe. Magically, the universe can expand. I don't know how. It doesn't make any sense to me. I think it disobeys the rules of physics, but there you go. But it does seem to me that physics and all the sciences do disobey rules in general as they go along when they see an exception. Hubble sees the universe seemingly expanding or moving outward, and so science says, well, it's expanding. Science will not say it's growing, because that just seems so weird. It seems like insane. How can the universe grow? I mean, that would assume that matter is created, but then you have the contradiction of, well, if matter isn't created, how do we have a universe to begin with? Did the universe just suddenly pop into existence by an action of the Wizard of Oz, or by magic, or just some magical thing? And then we come up with theories to explain how the universe could have popped into existence, singularities, and all the rest of this. I'm kind of a Sherlock Holmesian type of person. I like to see reality. Theories are all very nice, but as we observe history, we observe that the theories very often get pretty much shot down by the next generation of scientists. So here you have a problem. You have a universe that either popped into existence or evolved by a process that we don't understand, and this is the way it is now, and it's growing. And that's the alternate, that it grew and it continues to grow. So Sam Carey didn't get involved in this. He just looked at the evidence of geology in the 1960s, and he essentially said the Earth is expanding. There's so many proofs in so many areas of the Earth growing. There's so many proofs of the moon growing. There's so many proofs of Mars growing. There's so many proofs of all of this that I have trouble, if I'm going to talk about it, just talking about all of this stuff. So I'm just going to talk about one area, and then if you have any questions, then you can ask me about the other areas. We're just going to talk about differentiation because it's easier at the moment to just limit it to this little area. So the scientific community seems to be willing to say that the granitic rock of the continents has been made by a process of differentiation. Okay? There's some things that we know as factual. For example, the upper area of the asthenosphere, the couple of 100 miles, is denser than the area just below it. And one of the things that's interesting about it is that we seem to be getting basalt or basalts from that material right now. So you look at the continental plate and you go, okay, it's from differentiation. And then you look at the oceanic plate, which seems to be denser. The granitic rock is like 2.7 times the weight of water, whereas basalt is 3.3 times the weight of water. It's quite a difference. So if you think of a scenario, and this would be the scenario that I would suggest, an early Earth heating up. I know we don't want to say heating up because it's supposed to be cooling down, but early Earth, however it's heating up, just under the crust of a, let's say, a primitive crust of mixed granitic material, you have a molten area, which we have now, of mixed silicates. And so that melted stuff is going to differentiate. We all understand differentiation. It's, the lighter stuff goes to the top and the heavier stuff stays at the bottom, right? You got that. So you differentiate out of this couple of miles of melted rock from superheated gases, which does seem to be the only way to do that. You differentiate the granitic rock from the basalt. And so what happens is that your granitic rock either erupts to the surface in volcanoes or it underplates the upper crust with granitic rock, with layer upon layer of granitic rock. Assuming that this is what happens, and that's how we get all the continental plates, okay, by differentiation, which science agrees that's how we get it, then we have to understand that liquid, and that's what molten rock is, it's a liquid, it's opportunistic. That is, if there's an empty space, it'll fill it. And if there's an empty space over here, it will fill it. So what happens is that the differentiated granitic rock will fill the whole crust of the Earth just under the surface. And that seems to be what happened. Essentially, you've got a differentiated granitic crust under, and this is what Sam Carey would say, under the whole of a smaller Earth. Well, as soon as we hear that, we go, "Well, you're crazy. You're saying that the Earth grew. There's some kind of a process that's creating matter." But you can understand. I'm not talking about that right now because that's another topic. But right now, essentially, a opportunistic liquid material will fill in all the spaces. So if you have a crust and you're differentiating granitic rock, and it's not only a thin layer, but a thicker layer and another layer and another layer till it's miles and miles thick of granitic rock, it's going to make a smooth ball, essentially a smooth ball with a diffuse upper crust and granitic rock. At some point, that upper area that's melted or molten is going to run out of granitic rock because it's not getting deeper in its differentiation. It's not melting further down. It's got a certain level. Maybe it is going further down, but not to the degree that it's finding more and more. I mean, there is a little bit more of granitic rock, and it does seem to continue to come up. But essentially, you've run out of granitic rock. So you've made your granitic crust. 250 million years ago, the Earth seemed to have run out of granitic rock. And so now it had to erupt heavier rock. It had to erupt basalt. So 250 million years ago, in Siberia, we have what's called the Siberian traps. Siberian traps essentially was an eruption through the crust of basalts. These basalts spread out to an area in quite a long time of hundreds of thousands of square miles and destroyed nearly all of life on Earth. 99% of life, they say, pick your figure. Because the Earth ran out of granitic rock and now it could only bring up basalts. Now, since that time, the crust of the Earth has cracked. And the cracks, the pieces, the outer shell of granitic rock, the old shell, have moved, these pieces have moved apart. Now these cracks, or the basalts that are below, can come up the cracks. In fact, they do all around the Earth. They come out in the deep ocean. What happens is the cracks appear in the deep oceans, the deep oceans spread, the basalt comes up. Every once in a while, a little bit of granitic rock, but mostly basalt. So most of the oceanic plate is made of basalt, 98% of it. And so these cracks spread and spread and spread and spread. And so you have the oceanic plate, which is the second plate of the Earth. All the granitic rock is sitting on top of that, and it's broken apart. Now, if such a process happened, something would have had to happen, some other process would have happened inside the Earth to create new material for the Earth to get bigger, for all these cracks to appear and to spread apart, and for us to have run out of granitic rock. So we have, in fact, run out of granitic rock. The continental plates are sitting like tree stumps in the land on this basalt second crust, and those second crusts are continuing to spread. Now, the problem with that, and Sam Carey brought it up in the 1960s, is, of course, physics said, well, you can't make matter. And Sam Carey, being a geologist, he couldn't obviously couldn't come up with an answer to that. But he said, well, that's not the point. The point is that as a geologist, I'm observing all the geology, and the geology says the Earth was smaller and it got larger, whether it expanded or blew up like a balloon or whatever it is, got bigger, and now we just have basalt coming up in the deep ocean. That seems to be the case. Now, that process, that particular process, started about 180 million years ago. That process for reality is answer. Now, mankind suffers the ills of mankind. One of the ills that suffers of mankind is that it's localized. If you're an American or a European and you see that finally after Wegener pronounced that the continents pulled apart, that somehow, and once they were all together, you might, as an American, or Canadian, and a European, you might say, well, all these continents were together in the Atlantic, and because that's where you live. You say, well, and they were all together in the Atlantic, and they made this one big giant island. Well, the problem with this one big giant island is a multifold problems. There's this Pangea theory that was presented in the 60s, and the only person that really spoke against it, and then other geologists spoke against it after a while, was Sam Carey. Now, that is not to say that Sam Carey was alone in doing this. There were several dozens of geologists who agreed with Sam Carey. Nobody came up with the mechanism. Okay, my feeling was, as I was watching this as a young man, was, if Sam Carey is right, and just parenthetically, geology discovered subduction in the deep oceans. Subduction seemed to make an excuse for the readings of the continental plates, and that is that the oceanic plates in the oceans ducked under one another like I guess a snake eating its skin. Somehow, the Earth in 180 million years manages to eat 100% of its oceanic plate completely, including bays and inlets and all these various places. Somehow manages to eat the whole of its oceanic crust and regurgitate a new oceanic crust. Sam Carey found that to be a little bit amazing, but he couldn't really come up with an answer for it because he was, as I say, a geologist. So what he needed to do is he needed to go to a physicist and find a mechanism. How do you make new matter? How do you make new matter inside of a planet? The problem with that, of course, is that if geology turns against you, which they did for Sam Carey, then essentially Sam Carey is going to not find a physicist that's going to cooperate with him, because who would throw their career away in trying to find a methodology by which matter can be made at the core of the Earth? And so he failed, and his career failed until he died something like 5 years ago, holding on to his theory along with other people that held on to this theory. I decided early on that I would investigate this from a physics and from a point of view of all the other sciences, or as much as I can. And that's what I've been doing. Now, one of the things that you can see on the internet is you can see the videos that show the various spreads. And what I've run across is that there's so many proofs that prove this that it's almost like an encyclopedia of material. For example, and I'll just give you a few examples. 180 million years ago, when Pangea supposedly existed, according to those maps that you see on the internet and your geology book and all those various places in class, 180 million years ago, when all those continents were together in one giant continent on one side of the Earth, which I have to say looks a little silly. All those continents, first of all, they had to gather there. There is no process that would allow them to gather there, but if they got there, they couldn't come together. Because unfortunately, if you take subduction seriously, then you have to say, okay, you have one oceanic plate, and then you have another oceanic plate which cracked in the middle, and one side of this oceanic plate slid under the other side of the oceanic plate. Then you have what you'd call an abducting side and a subducting side. The abducting side never disappears. The subducting side can disappear. It can slide under the abducting side, but the abducting side can only go over the subducting side. That means if you were to bring two continents together and assume that there's subduction between the two continents, then yes, you can get rid of the subducting side theoretically, but you can't get rid of the abducting side. So you would have a giant, massive basaltic suture between the two continents. They don't exist. Nice enough to say it, but they just don't exist. Okay, that's number one. That's just the continents can't come together and become one big giant island. That's impossible. Physically, it's impossible. Here's another one. 180 million years ago, the sea level was 800 feet deeper than it is today. 800 feet deeper than it is today, makes of all of our continents, okay, covers all of our continents, two-thirds of our continent by shallow sea. That means that if there was a Pangea, then
we're having a hard time hearing you, Neal.
And why is that? What am I doing wrong?
I'm not quite sure.
You can tell me what to do, I'll do it.
Let's see here. Well, now we've completely lost your audio.
I am here. What did I?
Okay, well, I think I just muted somebody, so I think they may have been adding too much noise. But go ahead, yeah, we can hear you now.
Can you hear me? Okay. I'm sorry. If I did, whatever I did, I don't know what I did. I didn't touch anything, I swear to God. Anyway, so at 800
You need to talk slower.
I need to talk slower. Okay.
Yeah, because it's breaking up the syllables of your speech.
All right.
Does that make sense?
It doesn't make sense to me, but I will do it, and we'll do it. We'll try it. So 800 feet deeper sea level means that essentially a Pangea would pretty much look like the Philippine Islands. because it would be a whole series of islands. Even North America was split down the middle. The East Coast was underwater. The West Coast was underwater. The whole center was underwater. 2/3 of the North American continent was covered by water. Part of the principles of the Pangea theory is that the continental plates supported a life of dinosaurs and lizards that could migrate from continent to continent freely and appear on all 7 continents of the Earth. Well, if it was broken up like in a series of islands, how could this happen? It doesn't make any sense. These shallow seas covered 2/3 of the continental plate. So that's not possible. Here's another one. It's a little hard to understand, but when you start to investigate this, it does become realistic. There are no fish fossils in the deep oceans that are older than 70 million years old. There are no fish fossils in the deep oceans that are older than 70 million years old. How is that possible? The only way that's possible that I can understand is that it took the fish 100 million years to evolve to live in salt water. And that on the continental plate in the shallow seas, there was essentially, or very little, salt water. Okay. Now, where do we get salt water? Well, science has theories. There's so many theories in science, and so many of them could easily be just theories. For example, we know where the salt is. It's in salt domes. Yes, there's some salt on the surface in plants and other stuff, but essentially the salt that appears in the deep oceans is in salt domes down around where we find the oil. Okay, you got to dig down to find it. Now, one of the ways that we get salt in oceans, are you hearing me?
Yep, we got you.
Okay. One of the ways we get salt in oceans is when the continental plates crack apart, they break into salt domes. In the Gulf of Mexico, there are over 200 salt domes that have been broken into by the cracking of the continental plate. Now these salt domes would feed salt into these deep oceans. So if you have fish that exist on the continental plate, these fish would, of course, not be able to live in these new salty waters. It would take them an amount of time to evolve to live in salt water. So they would stay on the land. Well, one of the things that's true is that there are over there are over twice as many fish families that live on the continental plate than live in the deep oceans. Twice as many fish families that live on the continental plate than live in the deep oceans. And there are no fish fossils in the deep oceans that are older than 70 million years old. On the other hand, on the continental plate, there are fish that have lived as much as 400 million years. 400 million years on the continent. Yet, you'll find science, not that I hate science, but there's a lot of theories out there. Science will say, and you watch it on Discovery or whatever, this fish swam in Earth's oceans 200 million years ago. No, this fish or whatever you're displaying was found on the land, on the continental plate. It was not found in the deep oceans. It's essentially a lie. It's just the assumption is the fact that we found it in Utah means that it also existed in the deep oceans. Well, it didn't. And that's a fact. And one of the things I like to do is I like to deal with facts. I like facts. And I don't like expanding Earth theory. Facts are very, there's not that many. The good thing about facts is that you can depend on them. They're facts. I mean, maybe they'll be overthrown at some point, but theories, very fishy. So I like to go with facts. If there were no fish fossils in the deep oceans, and if when you go to your museums or wherever you see these fossils, every single one of them was found on the land, okay, on the continental plate. There's a story there. That's a fact, okay? None were found in the deep oceans. People will say, well, you don't want to dig in the deep oceans for fish fossils. Excuse me. They've been digging in the deep oceans for fish fossils since the 1930s. They've dredged and they've cored the deep ocean since the 1930s. In fact, just to give you a little history lesson here, in the 1960s, 50s going into the 60s, but in particular into the 60s, the geologists and the paleontologists digging in the oceans couldn't find a plate, oceanic plate that was older than 80 million years old. They couldn't find fish fossils that were older than 70 million years old. And it was a source of tremendous frustration. As time goes by, we forget these things. If they become part of history and they're not even referred to, especially if they disagree with the current scientific theory, it's forgotten. So I went through that time and I knew it at that time, and I was told it at that time. The geological and paleontological community were going crazy about the fact that they couldn't find fish fossils older than 70 million years old, and they couldn't even find oceanic plate that was older than, say, 80 million years old. We have found it up to 180 million years old now. So what they did was they called upon the U.S. Navy to help them plot the oceans. I have a map behind me over here, and you guys can find it on the internet. That you can, it's everywhere. It's called the Crustal Age Map. And it was made by this process, by the geological and paleontological community and the U.S. Navy, plotting the ages of the deep oceans. Those ages, and there, you have it on the screen right there. You can see in the Atlantic, you can see there's this nice even break. If you could cut this, which I have done, of course, and put the Pacific back together, which you can't do it. If you look on the right-hand side of the screen, okay, you see that triangle? On the right-hand side of the screen, that little triangle there is 180 million years old. It is the same age as the edge of the North American continent and the nub of Africa over there, which is where the Atlantic Ocean began to break apart. In the Pacific Ocean, that triangle on the right is the oldest ocean in the world, along with that one area in the Atlantic. That means that the Pacific Ocean is exactly the same age as the Atlantic Ocean. They both started to spread at the same time on either side of, strangely enough, the North American continent. You can't tell because they spread a slightly different way. The Atlantic spread differently than the Pacific. The Pacific left its oldest ocean right in that triangle, and that is the oldest ocean in the Pacific Ocean. So they both spread at the same time. A coincidence? I don't think so. Sherlock Holmes would say, I don't believe in coincidence. You will also see that that triangle would indicate that that was a three-way spread, that it on the left was Asia, on the right was the North and then South American continent, which spread later. Then there was Australia and Antarctica, which was at one up until 60 million years ago, which was one supercontinent. And then 60 million years ago, it started to break apart. You can see the break apart just below Australia going into Antarctica and circumnavigating the whole of Antarctica, okay? So there's a story here. If you read this story, one of the things that will tell you, that the story will tell you is both oceans, both the Atlantic and the Pacific, began to spread at the same time. Exactly, I'm sure it wasn't up to the day, but 180 million years ago. Before that, we didn't have these spreading oceans. So we had things like the Siberian traps. Siberian traps spread this basalt and it covered the land. But later on, as the oceanic plate started to spread, the basalt did not spread onto the land. But since these cracks were opening up deeper, then as they spread and the basalt and the superheated gases came up, they would come up in water. And the water would cool them down immediately. So it became a peaceful, calm process that goes on today. And all those red marks that you see going through the map of the Earth is where all these spreads are. Nice and even and regular, in some cases more, in some cases less. So this is not a process that began in one ocean. One of the things that happened was that Sam Carey, who comes from Australia, said, wait a second, guys. You're talking about you know, because you're North Americans and you're Europeans, like you're just looking at the Atlantic Ocean. What about the Pacific? I think the same stuff went on the Pacific as went on in the Atlantic. So he wrote 2 books. You can read the books, okay? But they are geological in nature, and because they're geological in nature, there's no reference to the mechanism. You know, he has some theories about it, but of course he can't do that because he's not a physicist. And who is going to join him in this theory from the physics community? Nobody. Why? Because it's a failed theory. And who is going to bet their life and their career on a failed theory? Who is going to join him? So just geologists who agreed with him from the beginning. I, of course, am not a scientist. I'm an artist, okay? And I can study. I can pick up a physics books just like anybody else. And that's what I do. That's what I pick up all these physics. And I've decided that if Sam Carey couldn't prove this, okay, from his point of view, then as a geologist, then the problem was that we were trying to solve a bigger problem than just the growing Earth. Because the growing Earth, the Earth can only be a microcosm of the universe. And if the Earth is a microcosm of the universe, you have to understand the universe and how it works. You have to understand all the planets. You have to understand all the suns. You have to understand all the moons. You have to get it, the whole picture. The only way you can do that is by studying all the sciences. Well, you can't go into a tremendous amount of detail, but there's an awful lot of detail you can go into, especially if you localize the problem into how does all of this work. Okay, so I'm not heavily into the math, I have to tell you, but I am heavily into the science, and I do love the science. And believe me, I'm not trying to shoot all of science down when I talk about these things. I'm simply trying to say we are besieged with theories, and we don't pay attention to facts. And if I can just show the facts, and then people can argue theories with me all they want, and I just stick to the facts, I'm going to be able to get a lot further. It's been a long time. I thought that I would solve this problem in a short time. It's taken me over 35 years.
So Neal, I did have a question.
Yes, absolutely.
So one of the new pieces of information we have is Pluto. So I was wondering, I heard some things about
down in the lower right over there. See that area in the lower right?
Yes, the heart.
That is a spread area. And one of the ways you can tell a spread area, and those of you who are interested, you can go to the moon photographs and you can go to Mars photographs. What's happened in our universe is that, in our solar system, is that smaller and smaller meteorites are striking. And it seemed to me for a long time that it was because of Jupiter. Jupiter was sucking up all the meteorites and protecting all the inner planets. I mean, many scientists call Jupiter the meteorite umbrella for the inner planets. Very realistic to think so, but you wouldn't think that it would happen out in Pluto. But the way you identify a timeline is you look at the size of the craters. Okay, the smaller the craters are in an area, the more its newer surface. I mean, look at Mars. You can see very easily on Mars, or even on the Moon. You get front side of the Moon. There are areas that filled with craters, and then there are areas that are big spread areas. But if you turn the Moon around, you look at the backside of the Moon. The backside of the Moon is covered with massive craters, partially because of the gravitational attraction of the Earth pulls at the Moon toward us, so the spreading happens toward us, and that's why you have spreads on the side of the Moon that faces us, but on the side that faces in the opposite direction, it's basically old craters. So that is old land. The same thing is happening to a certain lesser extent on Pluto. You can see in the lower right-hand side what they call the heart. If you had a close-up of that area, the amount of craters and the size of the craters are tremendously unavailable. And even scientists are saying now, yes, that's a younger area. That's a very, very young area, which is amazing to me because I'm shocked that NASA and those folks are agreeing with me here. But that's a young area. Well, how do you get a spread area that massive in the last couple of 100 million years? Because it's growing. And this is true. I have animations on Ganymede. I have animations on the Moon. I have two animations on Mars. that shows this spreading. On Europa, very simple spreading. In fact, it's so simple that even NASA shows it. I did a series of animations, one in particular, and I showed it, and then I sent a copy to NASA, and NASA actually does breakdowns, and they show you on the internet how you can like take sections of the surface of Europa and put them back together again, and they fit back together again like a jigsaw puzzle. So essentially, you have all these surfaces on all these bodies that you can actually see the surface on spreading. You don't want to look at Io because it's obviously molten and bubbling and crazy all the time. You don't want to look at Venus because it's just, you can't even see it and it's very hard to understand. But there are some places that are very, very clear. Our moon is very clear. Earth is very clear, except the water fell into the cracks. And if you just look, if you were to mentally take all the water off the Earth and just look at the oceans as spread areas, okay? Because water has almost nothing to do with tectonics, except that it cools off the basalt that comes up and it saves it from destroying the life on Earth. But essentially, the oceans are just spreads on the surface, just like you see on Pluto there. That's a spread on the surface. So you have these spreads, and on Earth, the granitic plates have spread out. Otherwise, if this weren't true, you would have to say, well, God came down and made these jigsaw puzzle pieces in which he drained all this differentiated granitic rock into these little puzzle pieces, which coincidentally fit together perfectly on a smaller planet. And he decided not to differentiate granitic rock in the deep oceans. Why? Makes no sense whatsoever. I mean, factually, it makes no sense. And once the geological community admits, and it has, fortunately, that granitic rock is based on a process of differentiation. Then differentiation, just like you're in your chemistry lab and you're putting oil and water together and you shake them up and the oil goes to the top. You heat, and remember, this differentiation only happens in liquids. So it only if you've got rock, it only happens when the rock is melted. So the rock in the asthenosphere underneath that melted rock is not going to differentiate. It's just going to stay. But the stuff that's melted and molten, the lighter rock, and I know it's odd to say that granitic rock is lighter, but it is about a fifth lighter than basalt. It will rise to the surface, and that's what it did, and it created a coating on the Earth. That is not to say that the Earth wasn't growing at that time and the coating on the Earth in the layers wasn't pulling apart. But you can see that pulling if you fly across the country. You can fly across the United States of America, and you can see the land pulled apart in so many areas that it is a process that you always see on the land. You can see it in Europe. You can see it in everywhere. You'll see one ridge. Okay, you see flat land. You'll see one ridge. It goes straight down. Then you have flat land under it, and then you go so many miles, and there you see another ridge going up and flat land above it. That land 300 million years ago pulled apart, just like the oceans pulled apart.
Neal.
You can take photographs.
Neal.
Yes, sir.
We have 8 minutes left.
Okay.
Can we go to questions?
Absolutely.
I have a question for you. Okay.
Sure.
My question is, when you talk about growing Earth, and I'm assuming you've had this conversation with mainstream scientists, correct?
Sure.
What do they say? What's their reaction to this concept that you present?
That I'm crazy.
Well, what's their main objection?
Well, according to their subject, their objection is within their subject. A physicist, if I said to a geologist, matter is made, he would say, no, matter isn't made. You're out of your mind. If I go to a physicist and I would say matter is made, a physicist would say, well, you'd have to name your terms here. I mean, yes, matter can be made and can be destroyed, and it really can't be made or destroyed. It can be changed. Okay, it can be changed from one thing to, it can be changed from energy into matter. For example, you have pair production. When I